Section 2.3 is continuity. So we need to discuss continuity because a lot of the calculus we're going to do later is only guaranteed to work on functions that are continuous or on parts of functions where they're continuous. We have to understand what this means so we don't accidentally try calculus later in a place where it doesn't work. So informally, you might even already have an understanding of this idea of continuity. A function is continuous, just informally, if you could draw it without picking up your pencil. And it's continuous at places, like a part of the graph. It could be continuous at a part if you could draw that part without picking up your pencil. So with that idea in mind, just informally, think about this graph. We saw this graph before. Can you think of where this function might not be continuous? So think about places where you would have to pick up your pencil if you were trying to draw it. So we're going to visit this function again in a minute. So there are really four kinds of discontinuities, but only three come up in first year calculus. So we're going to talk about these. There's a place on your notes paper where you see these three pictures, and you should write in the names of these discontinuities. So a place where you have a function, but it's just missing one single point. There's a hole in the function. That's called a removable discontinuity. A removable discontinuity. It doesn't matter if the hole is empty. It doesn't matter if there's a function value there at all, or if the function value is somewhere else besides where the hole is, anywhere there's a hole. Removable, we're going to talk about that. That means that we're going to be able to do some calculus later, even on these functions, because we'll be able to remove the discontinuity by filling in the hole. We'll talk about how to do that later. And then there are three kinds of essential discontinuities. A jump discontinuity. I'm guessing you can tell why we call that a jump. If you were walking along the graph and you needed to get to the next piece, you would have to jump up or down maybe. An infinite discontinuity, because your graph heads up toward positive infinity or down toward negative infinity, and the graph from the other side can't catch it. And then an oscillating discontinuity. You're not going to see come up, but there is a fourth kind. So make sure you labeled those three pictures on your notes paper. We're going to go back to this function. So if a function is continuous, any place you could draw it without picking up your pencil, then this function is discontinuous at the places where I would have had to pick up my pencil. For me, that's x equals 1. I can't draw that part without lifting up my pencil. And also x equals 2, there's a hole. So two discontinuities. Or there's a place on your paper where I ask you to say where this function is continuous. I would say this function is continuous on the entire interval from 0 to 4 inclusive, except for x equals 1 and x equals 2. Just in case there was any confusion, at the endpoints, it's a little bit like when we talked about limits. There's no domain values to the left of x equals 0 or to the right of x equals 4. So you don't have to worry about saying that the function's not continuous because you have to pick up your pencil to end the graph. We would say this function is continuous on the entire interval. I'll write it out. 0 is less than or equal to x, which is less than or equal to 4. And I would have to write out in words except x equals 1 and x equals 2. All right, so now go back to everything you know about reading a graph from pre-calculus and what we've talked about so far about investigating limits, left-hand limits and right-hand limits. And at the two places we talked about, which are x equals 1 and x equals 2, you're going to find me these three things. The limit as x approaches that number from the left, the limit as x approaches that number from the right, and the actual limit. And then pause that and try the three questions down below. So you're going to use the graph here and your work on this problem to give me an example of each of those three down below to say whether they're true or false. All right, so maybe you've connected this back to what we've been talking about, this idea of a well-behaved function. Let me go to this guy. So the places, just informally, the places where I know there's a discontinuity because I know I'd have to pick up my pencil, I find that I have something happening. Either there is no limit because the function approaches two different values from the left and the right. Or the limit exists, but the function value doesn't match. So well-behaved functions have behavior that we can predict. So they approach the same value from the left and the right, and they actually do at that x value what we were expecting them to do. So this is the formal definition of continuity at a point. There's a place for you to write this in at the top of page 2, so that backside of the first page of your notes. So a function f is continuous at x equals a if the limit of f as x approaches a is equal to the function value at x equals a. And here you can see the notation for that. Make sure that gets written in on your notes. And you can match that back up with the picture. So you can see at x equals 2, the limit exists and is equal to 1, but the function value is 2. So the limit does not equal the function value. That's why, that's a calculus way I can say for certain, for sure, or for certain, I combine them, that there's a discontinuity at x equals 2. So notice the saying that the limit is equal to the function value implies, number one, that the limit exists, and the limit's only going to exist if the limit from the left equals the limit from the right. And it also implies here that the function value must exist. So there must be a colored in dot somewhere for us to be able to say whether a function is continuous or not. So we're going to use that definition that we just wrote. The limit as x approaches a of f of x has to equal f of a to answer this question here. Can I choose the letter c, the value of c, so that this function, a piecewise linear function, is continuous? Well, what did I just learn? I just learned that the function f is continuous at x equals, in this case, the only interesting x value to explore is this x value 2, because to the right of 2 I have this, which is a linear function and lines are continuous, and to the left I have this linear function and lines are continuous. So what am I going to choose c, so that right at the place where x equals 2, my limit from the left and the right are equal, so that the limit exists, and the actual function value is also equal to that limit. So let's do this. I need this to be true then. I need the limit as x approaches 2, my a in this case is 2, of f of x needs to equal f of 2. Okay, well I can tell what f of 2 is because I know how to read these piecewise function notations, and I know that this guy, the place where there's the or equal to sign, that's how I'm going to find the actual function value when x equals 2. So I know f of 2, I'm going to get by replacing that x with 2 is going to equal 2 plus 3 equals 5. So I need the limit as x approaches 2 of f of x to equal 5. But what's the limit as x approaches 2? Well, I have this problem, which is if I don't pick the right value of c, I'm going to have two lines that approach a different y value. So I want them to approach the same y value. That's going to make my limit exist, and I'm going to make sure that that limit is equal to 5. So I need the limit as x approaches 2 from the left of f of x to equal the limit as x approaches 2 from the right of f of x. So here, to make that happen, this is like saying the limit as x approaches 2 from the left of, well, to the left of x equals 2, which rule is in charge? To the left, it's this guy. I need x plus 3 to equal the limit as x approaches 2 from the right of, I have a different rule in charge, that's cx plus 6. So I'm going to come to a whiteboard. All right, so I copied that from down below. And now these two limits I can evaluate using substitution. I'm going to let x equals 2, so the limit as x approaches 2 of x plus 3 is going to be 2 plus 3. And I'm going to need that to equal, as x approaches 2, cx plus 6 is the same as 2c plus 6. I need those to be equal, so I need 5 to equal 2c plus 6. I'm going to solve for c. That's going to be, I'm going to subtract 6 from both sides, so negative 1 equals 2c, and c equals negative 1/2. So if I choose c to equal 1/2, the limit as x approaches 2 from the left will be 5. The limit as x approaches 2 from the right will be 5, and that's equal to the actual function value, which will be 5. If those three values are all equal, then my limit exists and is equal to the function value, and my function must be continuous now at x equals 2. All right, so we have two last things to talk about in this video. One is, how do you remove a removable discontinuity? So consider this function, x cubed minus 1 divided by x squared minus 1. I know I'm going to have a problem in my graph any place where I have a divide by 0 problem, so any place where the denominator equals 0. That happens at x equals 1 and also x equals negative 1. There are two solutions to x squared minus 1 equals 0. So we're going to explore the place where x equals positive 1, because this is where we have a removable discontinuity. We'll show you in a minute how you can decide. So what we've been asked to do is write a new function that looks like f everywhere, except at the place where x equals 1, we're going to find the hole and we're going to fill it in. So we're going to make a function that is continuous at x equals 1, but is otherwise identical to this function. So here's what we're going to have to do. For a function to be continuous at x equals 1, the limit as x approaches 1 must equal f of 1. So right now, f of 1 is undefined. If I replaced x with positive 1, I'd have 0 divided by 0, which is undefined. If I graphed this, there would not be a y value to fill in at x equals 1. But if I can find the limit, then I can choose a value to fill in the hole, and that's what I'm going to do. So here's my technique. We know this technique. It's the same thing we did to find the limit for not well-behaved functions. So to find the limit as x approaches 1, I'm going to factor and cancel where possible. So this factoring pattern for difference of cubes, I hope you might remember it. It doesn't really come up in calculus, so it's not going to be a super huge deal, but x cubed minus 1 factors as x minus 1 times the quantity x squared plus x plus 1. That's this factoring here that you can see. The denominator, I hope you can factor. And we'll notice we have a matching factor x minus 1 in the numerator and the denominator. So the limit as x approaches 1 of x cubed minus 1 over x squared minus 1 is the same as the limit as x approaches 1 of x squared plus x plus 1 over x plus 1. Now that I've been able to cancel out that x minus 1 factor, I don't have a divide by 0 problem. Now I can use substitution. So I'm going to replace all my x's with 1s. My numerator turns into 1 plus 1 plus 1. My denominator turns into 1 plus 1. And I have a limit. I've actually been able to compute the limit, even though I can't find the function value. The limit is 3 over 2. So what this means is that if you actually graphed this function on a calculator, or maybe it was a pre-calculus assignment and you had to make this graph, you would have an open hole in your graph and the coordinates of the hole would be 1, 3 over 2. So that tells me that right now my function is undefined when x equals 1, but if I could just define it at that place to fill in the hole, my function will be continuous at x equals 1. So it sounds like it's going to be a very complicated thing to do, but really all we do is make a piecewise function. And, one piece is going to be the piece that we knew about, because we want our function to look exactly like this everywhere it can. But notice it's not defined for the place where x equals 1. So I'm going to add a piece. But the only job of this piece is to put one single pencil point in at that hole. So this one piece, the only job it does is it makes 1 point at 1, 3 over 2. But that fills in the hole and makes my function continuous. So there's a note here. What we did is we filled in the hole at the place where this function has a hole. This function also has a vertical asymptote, which is not a removable. It's an essential discontinuity, which means there's nothing you can do about it. It's essential to the function. You can't fix it, can't fill it in. So we were able to fix one discontinuity. There's another one that we would not be able to fix. I'll show you a picture. So if you zoomed in on the original function, there would be a little hole right there. But our new function colors in that hole, and now our function is continuous. But notice this vertical asymptote. You'll never be asked to fill that in because there's no way to fill in a vertical asymptote. That's what makes it an essential discontinuity. Okay, so one teeny tiny last idea at the top of page 3. If a function is continuous, well, if you have two continuous functions and you add them together, the resulting function will be continuous. If you multiply two continuous functions together, the result is also continuous. So continuous functions can be added, subtracted, multiplied, multiplied by a constant. The new function is continuous. And that also applies to composition. Composition is when you make one function the input to another function. So, for example, this is the composition of the sine function and the x squared function. Well, sine of x and x squared are both continuous functions. So if I compose them, if I sine x squared, or if I take sine and square it, that's the other way you could compose those two functions, that result will be continuous as well.